Okay, so last time we had introduced and talked a lot about the cross ratio, but I'm going to talk about it a lot more today because I'm going to basically spend the entire class talking about what it is that makes cross ratio so awesome. Okay, so um, what was the thing that we saw last time? So what we saw last time is if you were to apply the cross ratio to, or rather apply projections to the cross ratio. So there were three basic types of projections, right? So there's the projection that ends up being a translation. So sending a point on a projective line to x plus L, so it shifted some amount. So that remember this was projecting from a point at infinity. There's projecting from a finite point, which ended up scaling the projective line, so x is sent to kx. And then there was the inversion projection, which is the case where you're projecting from some finite point, but say the lines in question are no longer parallel; they intersect. Okay, so to get x being sent to 1 over x, of course, we use the very simple. We projected from the origin. And we had two lines that were perpendicular to one another. Anyway, okay, so but we saw in each case that applying each of these projections to the cross ratio preserved the cross ratio, so it didn't affect the cross ratio. So the cross ratio is a projective invariant in that sense. Okay, so then what we're going to show today by the end is that essentially it's basically the only invariant. Okay, so this is an invariant. We're going to be using this word a lot, invariant. So this is an invariant of linear fractional transformations. I.e., and remember, linear fractional transformations are in one-to-one correspondence with projections. So every projection is realized as a linear fractional transformation, and vice versa, right? Every single linear fractional transformation is a projection on a projective line. So i.e., it is an invariant of projections. It is a projective invariant. Of a line. All right. Okay. Now, the question is it the only one? The answer is no. But, there's a big important but here. But, it is basically the only one. And I'll put only in quotes too. Okay. So, what do I mean by these two terms that I've put in quotes here? So what are some other examples? So some other examples of projective invariants. And remember, like I said, because I don't want you to get completely lost in this terminology when I say this, because it's very, very easy. Mathematicians start using this kind of classifying language, and especially when talking about invariance in this way. This has been the approach of math for the last like 60 or 70 years, sort of, to adopt a certain type of terminology here, and it can hide kind of a lot of what's going on if you don't drill into your head what I mean by this. So a projective invariant is going to be an invariant of projections, meaning that it is a quantity that is unchanged by a projective transformation. So in the context of a projective line, which is what we're talking about here, so projective invariant of a projective line. In the context of a projective line, this would be some quantity that is left unchanged okay, by projections, okay, which are the, the thing that give projective geometry its name. So the question then is, what, as I mentioned last time, this quantity couldn't have been length because length doesn't make sense projectively, right? So on the projective line, length doesn't make sense because remember, all of our constructions, if you think about it as constructions, they involve a straight edge only. So there's no way of measuring lengths, right, in projective geometry. So that quantity couldn't have been lines. It couldn't have been angles. And so what is it? Well, it's the cross ratio. And as we'll see, this is, tied into the notion of collinearity. So basically, in projective geometry, the notion of collinearity or incidence is the fundamental notion. Whereas in, say, Euclidean geometry, the fundamental notions are things like length, right? That is the distance between 2 points is the fundamental notion. Or the angle between 2 lines, that's another fundamental notion. And those Euclidean transformations, right, in that took the place of projective transformations were the isometries that we talked about. And so what quantities in Euclidean geometry are the isometry invariants, right? What quantities are invariant with respect to the isometries of, say, R2? Well, the notion of length, the notion of angle, right? These things are preserved. So those would be the invariants in Euclidean space. Okay, so this cross ratio is taking the place of, those more familiar quantities that are invariant. Okay, so anyway, what's some other examples of projective invariance here? So there's cross ratio, say, cubed. There's cross ratio plus 5. Okay. I wrote plus 1 because that's what the textbook wrote, but I said plus 5, so we'll do plus 5 here. And so on. So, I am begging the question here of, well, what I'm implying is that, yeah, like cross ratio cubed is definitely different than the cross ratio itself. Cross ratio plus 5 is definitely different. But both of these, of course, involve the cross ratio, and it's like you had a function and you stuck the cross ratio in it. So, in fact, that is the case. It turns out, go ahead and spoiling the fun here, that any projective invariant of a line is some function of the cross ratio. That's the important bit. Okay. All right. So, there are lots of important properties of cross ratio that we're going to talk about today. So before we get into this, there are many important properties of the cross ratio that we need to discuss before getting on to this last thing I want to talk about. Okay, so all of these are going to have names because each one is an important thing to keep track of. Okay, so first property that we're going to discuss is what's called fourth point determination. So this is fourth point determination. What does that mean? Well, let me write out the full statement here. So given any 3 points, say P, Q, and R, in the real projective line RP1, okay, any other point, any other point, say X in RP1, is uniquely determined by its cross ratio with these other 3 points. So this is uniquely determined by its cross ratio. Well, I'll just write it out rather than saying it in words. P, Q, R, X. Okay, which we'll call Y with P, Q, and R. Okay. So this is what's meant by fourth point determination. Given any 3 points, any other point you want to come up with is uniquely determined by this cross ratio. So, said in another way, given these 3 points, if we knew that their cross ratio with a fourth point is Y, okay, then this point X is uniquely determined. There's only one choice there. Okay. All right. Okay, so why is this true? So a quick proof of this. This turns out to be a pretty simple thing to prove. This statement is true because we can solve the equation y is equal to, I'm just going to write out the cross ratio here, so y is equal to r minus p x minus q over r minus q x minus p uniquely for x. Right, uniquely for x in terms of p, q, r, and y. Okay. All right. Okay. So if you don't believe that, you can have a look at how you might actually do that, right? So when you could just, if you clear denominators here, multiply this out, isolate the x terms, you're good to go here. Okay, you could solve this for x uniquely in terms of every other letter that shows up here. Okay, so that's nice. That's a nice fact. As I mentioned before, the next fact you should compare with what was true about isometries in the plane. Okay, so contrast this with what we did in the plane before, talking about Euclidean isometries. And so this is the existence of three-point maps. What is a three-point map? A three-point map is a transformation that maps 3 points in RP1 to any other 3 points you like. Okay. What this says intuitively for us is that any projective invariant we would want to come up with could not be a projective invariant of 3 points alone. The reason for that is we can come up with a projection that projects any 3 points you like onto any other 3 points you want them to go to. Okay, so then the invariants of 3 points are just not going to be very interesting because of that. Okay, there's way too much freedom in how you can map those 3 points around projectively. So we'll see exactly what we mean here. So given 3 points, so given 3 points P, Q, R, in RP1 and 3 points P prime, Q prime, R prime in RP1. There is a linear fractional transformation. That is a projection, right? It's just more convenient to deal with projections as linear fractional transformations than abstract projections. But in terms of drawing pictures, of course, we can still consider them as abstract projections. Okay. So there's a linear fractional transformation, call it F, sending PQR to P prime, Q prime, R prime, respectively. Okay. All right. So, how do we do this? Maybe I need more picture here. So proof, we'll draw a picture. Okay, we'll draw a nice picture. Let me get my straight edge over here. Okay, so let's say we have one copy of RP1. Okay. So let's say we have one copy of RP1, and let's just lay out our points. P, Q is here, we'll say, and maybe R is closer to Q than Q is to P. All right, so there's what we have. Well, we can actually arrange our other copy of RP1, right, our other projective line, in a way that wherever P prime is on that projective line, we just match it up. Okay? We just match it up like this. Okay. All right. And if we do that, right, then wherever, say, Q prime maybe is here, and maybe R prime is like down here, then what do? Well, we draw in these lines. Maybe my R prime needed to be further away for this picture to work out on this page. Maybe I should have drawn here. I'm gonna have to extend my page a little bit. Here we go. Right here, I'll extend my page so that we can see this. Okay, so what do we do here? Well, the idea is that I draw in these lines. Well, I didn't have my straight edge far enough up, so I draw in these lines. All right, and here's more. I'm gonna have to move my straight edge. And okay, so I draw in these lines in this way, and what I have done here is, in reverse, I have found a point P, right, such that projection from point P maps P to P prime, right? We lined those up. It maps Q to Q prime, and it maps R to R prime. Okay. And I could have done that, of course, with any 3 points. The idea is wherever, you didn't have to do it with P here. You could have done it with Q or R just as well. The idea is wherever those points are on the projective line, line up one pair of them. Okay, so arrange your projective lines in a fashion where you've matched up two of them, and then you can use the other two lines that must intersect at some point, right? Maybe they intersect at a point at infinity, and you can think about what that picture would look like if you did it that way. But you're going to have 2 points, or 2 lines that intersect. They determine a point such that projection from that point onto these projective lines is exactly the transformation that you want. So you can always arrange your copies of RP1 like this, and so projection from this point such that these 2 lines meet that's the mapping that you need. So boom, you're done. Okay, nice. Proof by picture is always a nice thing. Now I can get rid of my extendo page. Okay. All right, so that's the second thing. So this is an important thing to know because it tells you that projective invariants of 3 points are just not interesting. All right, so then the next thing is from this construction, you might have guessed that these 3-point maps are actually unique. So this is uniqueness of 3-point maps. This is what our third property. So uniqueness of 3-point maps. Okay. So exactly one linear fractional transformation sends P, Q, R to P prime, Q prime, R prime, respectively. Okay. All right. Why do we have this? Actually, we get this by 4-point determination. So, quick proof. Well, we'll say any linear fractional transformation sending P, Q, R to P prime, Q prime, R prime must also send any X to X prime having the same having the same cross ratio. Right? Must send some point X that is not one of those things to an X prime such that P, Q, R, X is equal to P prime, Q prime, R prime, X prime. Okay. And this is since linear fractional transformations preserve the cross ratio, right? Since cross ratio is a projective invariant, this is the definition of that. All right, but we proved this, of course, on Monday. So since linear fractional transformations preserve the cross ratio. Okay. But this X prime has to be unique, right? Well, what does that mean? It means if you have a linear fractional transformation sending P, Q, R to P prime, Q prime, R prime, then any other point must get sent to this X prime in a unique way. There's not another choice here, right? So there's exactly one way to do it, right? But X prime is unique by 4th-point determination. Okay. i.e., there is exactly one such F. Okay. Okay. All right, so that's nice. Not only do 3-point maps exist, they're actually unique. There's a unique way to do this. You may have guessed that just from the way this construction went, that there would be exactly one way to do this. But anyway, that's the idea. Okay. All right. So what else do we need before the last fundamental fact about the cross ratio. So this is the characterization of linear fractional maps. Okay. So what I'm about to write, and me calling this the characterization of linear fractional maps, tells me that the cross ratio gives us another way of completely characterizing, that is completely describing, right, in every possible way, leaving absolutely no ambiguity here, what linear fractional maps are. Such that in an alternate universe, I could have used this as my definition of linear fractional maps. Let's say that, I kind of was thinking in reverse, and I came across the cross ratio before I even thought anything about, projective transformations, and came across cross ratio before I ever thought anything about linear fractional maps, and I just defined the three words linear fractional transformations to mean this thing that I'm about to say. Everything would have worked out exactly the same. Okay. All right. Instead of me defining linear fractional maps to be ax plus b over cx plus d. Right. That's what I'm saying. So what are the linear fractional maps? Was another way of thinking about them. They are exactly the maps of RP1 that preserve the cross ratio. So they are exactly the maps of RP1 that preserve the cross ratio. So what this means is, just to repeat what I just said, if instead I started with the cross ratio and I said, you know what, I just love the cross ratio, I love how it works, and I'm going to define this to be my fundamental quantity that I care about. Okay, and now I want to investigate which maps of RP1 fix the cross ratio, which maps of RP1 preserve the cross ratio. Well, it turns out those maps are exactly the linear fractional transformations, no more, no less. Right? I get every single linear fractional transformation, and I don't get anything extra that is not a linear fractional transformation. Okay. Okay, so let's prove this, that anything we get here is a linear fractional transformation. So we know from Monday's lecture was what? Lecture 20. Oh man, this is meta. I'm referencing the actual lecture number. So we know from lecture 20 that linear fractional transformations preserve the cross ratio. Okay. Okay. So we know that from lecture 20, linear fractional transformations preserve the cross ratio, i.e., right, if f is a linear fractional map, then the cross ratio of f of p, f of q, f of r, f of s is equal to the cross ratio PQRS, right? For all PQRS. So for all PQRS and RP1. Okay. All right, so this gives us one direction, right? So linear fractional transformations preserve the cross ratio. Now we want to show that if a map preserves the cross ratio, it is a linear fractional transformation. So conversely, suppose a map F preserves the cross ratio. I'm not going to write this condition again. So i.e., let's say it satisfies condition star. I'll call this star. So i.e., f satisfies star. So it satisfies star, which is true for all points PQ, or any 4 points PQ, RS, and RP1. Okay. Now, by the existence of 3-point maps, you can find a linear fractional transformation that agrees with f on, say, the first 3 points PQ and R. So by existence of 3-point maps, we can find a linear fractional transformation G. So f is not a linear fractional transformation necessarily. It's just a map. So suppose a map f, not necessarily linear fractional. We want to show that it must be linear fractional if it satisfies star. So suppose some map f satisfies star, this condition, that it preserves the cross ratio. By the existence of 3-point maps, we can construct a linear fractional transformation G that maps P, Q, and R to f of P, f of Q, and f of R. Right? We can find a linear fractional transformation G that agrees with f on P, Q, and R. So another way of writing this, of course, i.e., G of P is equal to f of P, and G of Q is equal to f of Q, and G of R is equal to f of R. Right? And we find that by mapping, using the 3-point map, PQR to f of P, f of Q, f of R, projecting, right? Using that projection that we constructed when we did this 3-point map. Okay. Okay, but f preserves the cross ratio. But f preserves the cross ratio. What does that mean? Since f preserves the cross ratio, right, this 4th point, G also has to agree with f there, i.e., G agrees with f on S as well. So G also agrees with f on S, i.e., G of S is equal to f of S. Okay, so this is by unique 4th point determination again, right? This is by unique 4th point determination. Okay. But now we've constructed a linear fractional transformation G that agrees with f on all 4 points. Right? So it agrees with f on any 4 points of RP1. What does that mean, though? It means it agrees with f everywhere. Thus, G agrees with f everywhere. So I started with the function f that preserved the cross ratio. I constructed a linear fractional map that agreed with f only on the first 3 points, but then that led us to say that it actually had to agree with f on all 4 points there. But f preserving the cross ratio means that G has to agree with f everywhere. So any point of RP1 you consider f mapping to, G would agree with it there as well. Okay. And so what does this mean? G is equal to f, but G is a linear fractional transformation. So f is equal to G, thus is a linear fractional transformation. And that's it. Okay, so that proof is a little trickier than the others that we've done, but it used everything that we had done before this. Okay. All right. Now, we come to the main thing, the main purpose of all of these properties that we've been mentioning. All these properties are nice on their own, but our main purpose is in what we're about to say. Okay. All right. And so note the existence of 3-point maps. Okay, it says that since any PQR in RP1 can be sent to any other 3 points, say P prime, Q prime, R prime in RP1 by linear fractional transformation. Thus, any invariant of triples of points must have the same value for any triple. So it's useless, right? It's trivial. It's pointless. Okay, because projectively, any 3 points can be sent to any other 3 points. So talking about projective invariance of 3 points is useless. Okay, so projective invariance of 4 points, however, well, we already know the cross ratio is an example. And in fact, as I've said, it is the fundamental example. Okay, so it is basically, in some sense, the only one. And exactly what we mean by that is the last, where did I label these things? Characterization of linear fractional maps. I didn't label that number 4, so maybe I'll stop the label here, and I'll just say the fundamental invariant. Okay, so as we said, invariants of triples are pointless to talk about because they're trivial, but invariance of 4 points in RP1, we already know the cross ratio is 1, and it's not trivial. It does have different values, but it turns out it's basically the only one, and what we mean by that is exactly this. Any invariant of 4 points is a function of the cross ratio. Okay. Okay. So, let's prove this. This will probably be all we have time for today. So, let I for invariant. So, let I of PQRS be an invariant of 4 points. So, this be a function that is an invariant of 4 points. That is an invariant under linear fractional transformation for these 4 points. Okay. Okay. So let IPQRS be a function that's an invariant under linear fractional transformations, i.e. I of f of p, f of q, f of r and f of s is equal to I of PQRS for all linear fractional, or for any linear fractional f, for any linear fractional transformation f, right? So if I apply linear fractional transformation to this invariant I in this way, I get the same thing as just applying I to PQRS. Okay. I.e., well, so I.e., use capital I here. So i.e., I has the same value on all quadruples, say P prime, Q prime, R prime, S prime, that result from PQRS by linear fractional transformation. Okay. But it turns out that we get even more than this. All right. So it turns out we have even more than this. So what is this even more? It turns out that I has the same value on all quadruples P prime, Q prime, R prime, S prime, with the same cross ratio as my original quadruple. Why is this the case? So this is an important step here, and is recognizing this. Okay. Well, the answer is because any quadruple P prime, Q prime, R prime, S prime results from PQRS via linear fractional transformation. Okay. But why is that the case? Okay, so quick sub-proof here. By existence of 3-point maps, so by existence of 3-point maps, we can send PQR to P prime, Q prime, R prime by linear fractional transformation. We'll call F. And by uniqueness of 3-point maps, F also sends S to S prime. Right? It's the unique point that makes PQRS, or the cross ratio of PQRS, equal to the cross ratio of the transformed quadruples P prime, Q prime, R prime, S prime. Okay. But this gives you the result. Okay, this thing that I've underlined is actually exactly what we're trying to prove. Why? Well, since I has the same value on all quadruples with the same cross ratio, we can view it as a function of the cross ratio. As a function, say j, of the cross ratio. Defined as j of the cross ratio PQ RS is defined to be the value of I on PQRS. So we started with a function I that that was preserved by linear fractional transformations, and that led us to say that this actually has to be a function of the cross ratio. Okay, and the only thing that would be left to check here, if you didn't believe, is that this is actually well defined. Meaning, what does it mean for a function to be well defined, right? It just means that there's no ambiguity here. So this thing makes sense so long as, I matches up with, if I know the cross ratio of these 4 points, then I should know the value of I on the 4 points. But that's exactly what I said in this underlined bit, right? That it is sufficient to know the cross ratio of the 4 points to know the value of I on those 4 points. So this means that we could just think of I as being a function of the cross ratio. So that's it. And so we've shown that the cross ratio is basically it. It is the fundamental invariant of RP, or of 4 points in RP1. Okay, so the cross ratio is what gets the job done. And it is this is why, we're not building it up too much when we call it the fundamental invariant, because it really is, in some sense, the key thing. It's the key quantity, right? It is the analog of like length, right? For instance, in Euclidean geometry that you're used to. So I don't have time to get into it today, so I think I'll stop here. But next time I will go over a couple of peculiar examples of projective planes, and then we will start with our next chapter, which is the last chapter of this third pillar, which is the geometry of projective planes, and in particular, as we'll go over then, what is going to be our main goal is building coordinates not from outside, but from inside. So in chapters 3 and 4, we brought in coordinates and put them on our space from outside, right? We did this very Cartesian argument of bringing in the numbers for the coordinates from outside. But it turns out there's a way of doing this without bringing them in from the outside. And I'm using scare quotes there, but we'll see exactly what I mean by that when we get to it. So anyway, I will see you all Friday. I'll be making some announcements, so pay attention to the course page. But anyway, I'll see you all on Friday.